ah, okay, can you hear me? Cool. Okay. And I want to check that whether the hopping is working very well. Yeah, I think so. Yeah. Okay, so welcome to our tutorial on historical learning in machine learning. I'm Sanghyuk from Naver AI Lab. And I think it would be better to start the tutorial now because this is 4 p.m. And I think people will come here about in 5 minutes. So let's start very slowly. Okay, so this is the outline of our tutorial today. So we are about 2 hours tutorial. So I'm the first presenter. So I will start from the introduction to circle learning, about 20 minutes, including the question and answering session. And then Yonghan will present understanding circle learning through the lens of causality and invariance. So it will be about 30 minutes talk. And then we will have 15 minutes break. So it is the official schedule of the conference between 5 p.m. to 5:15. Then Kyungwoo will present learning invariant representations about 30 minutes. And then the final part will be how to mitigate short learning in practice and future research directions by me. Okay. So let's start the introduction section. So again, I'm Sanghyuk from Naver AI Lab. And thank you for coming today. The machine learning, or maybe we can call this one as AI, opens a new stage of automation and application. So for instance, this is pose estimation. So input is an image of person, and the output is the coordinate of the joint of person, like the where is knee or where is arm. And this is another example, object detection. So input is again image. So input is pixel of the images, like 10,000 by 10,000 pixels. And the output is the location of objects in the image with the bounded boxes and labels. And the last one is face recognition. Here is again, input is image of people, and the output is the coordination of face of image, face of this image. Another interesting one is automatic code writing by Copilot. So this is a application deployed in GitHub right now. As far as I know, it will be changed to the paid version in next month in August. Right now, this is a free trial, so you can try one this during one month. So the spec is very simple. When you type the comment here, and when you type the title of the function, then it will make some automatic code without any template or without any guidance. The last one is self-driving car. So this is a combination of modern computer vision and machine learning, like the line tracing, because we have to trace the correct line instead of the wrong line. And the other one is like semantic segmentation for self-driving. So we have to know that whether this is car or this is tree or people, right? So it is very important to make some combination of these various techniques of computer vision or machine learning. The problem is this AI often cannot understand the problem itself. So for instance, here, an object detection model is very easily fooled by semantically meaningless patch image. So this is an image. So this is the meaningless patch image. So you can see that when this guy moved this patch image to the another guy, it failed to detect person class because of this dumb patch. So this is a type of adversarial attack, physical adversarial attack using some universal patch. So it means that the object detector not only focusing on person or some object, but it also focuses on some undesirable meaningless patch image here. The other one is, so Copilot is very brilliant and very awesome, but it's sometimes just memorizing training data set rather than thinking about the given comment or given description of the function. So this is an example. When you type the Xeno Python, it just memorize and repeat the true Xeno Python. So this is not we want, you know. Of course, one can argue that it is, you know, it is feature, not a bug. But you know, whatever a human who don't know about Python will not make the same comment like this, right? Okay, the last one is my favorite example. So this is an self-driving car example. So this self-driving car think this Burger King sign is a stop sign. So it's going to stop in front of the Burger King sign, right? So this is very fun example. Assume you are in the car and I mean, it is quite embarrassing if your car is stopped in front of the Burger King, right? Because the car think this is a stop sign. So why this happened? So in this tutorial, of course, there are a lot of interpretation of why this happened. But in this tutorial, we are focusing on easy to learn shortcuts. So machine learning models often rely on easy to learn shortcuts without understanding the problem itself. So this is an example. So this is an example of visual question answering. So the task is answering a text question for the given image. So question is, what color is the banana? And for this image, okay, this is yellow, right? For this image, this is green, right? But you know, in the data, most of the bananas are yellow. So rather than looking at this image, we can just answer the question without looking at the image, but just repeating, this is yellow. So in this case, a VK model often only focusing on text image, text question without looking the image. So we say that when a model does not make a decision based on desired feature, like the considering both question and image, in this case color, but undesired features, like the ignoring images. In this case, we say there exists a short-term learning problem. And there are more examples when short-term learning happens. But let's focusing on the first example. So this is very famous computer vision dataset, MS COCO dataset. So this is, you can see that this is common objects in context. So this dataset is about the object. So most of the images, I mean, all of the images contains some specific object, like ship here. So when you check images with ship, you can see that even though there is, you know, a lot of grass here, people usually annotate, I mean, the captions describing the animals instead of the green hills, right? So you can see here cow grazing in a field. Some white sheep are working up. 2 sheep grazing, you know. So assume you are a machine and you don't know about, you know, you don't know nothing about the structure of this image. You know, the machine only get the numbers, pixels of the images. So it is almost impossible to, you know, expect that machine truly understand what is the object and what is the background. But your data set, I mean, your training images are mostly about describing some animals where sheep are grazing. In this case, when you give to machine these types of green hue on the image, then the machine will say this is grazing sheep because the machine never think about what is sheep and what is green hue. Okay, so this is another interesting example. So this is a case of automatic job interview. So this machine determines five different criteria of whether interviewee is good to accept or good to reject. So it is very important question. Is the machine truly focusing on how the interviewee answers the question? Because this is what you want for during the interview. So we expect a machine interviewer to be fast and accurate because that is what we expect for machine instead of the human. And we expect this is cheap and convenient because humans are usually expensive. That is our common myth. And it is reproducible and objective. It means that not biased because it is typical to say that human interviewers can be easily biased, but machines are not biased because they are just machines, so they are objective. That is our myth and our desired feature, right? So let's back to the question again. So is the machine truly focusing on how the interview answers the question? So this article investigate the question by hiring a professional actress and letting the actress act on interview. If the machine truly understands the answers, different appearance do not affect to the result, right? Let's see. This one. Okay, so this is what they did. So this actress acts some interview about 1 minute. Then the machine will give us some scores, right? Okay, so now think about when she wears glasses. So surprisingly, this is very surprising, right? Because this is original and this is with glasses. You can see that the machine changes the scores a lot. It means that me on glasses and me without glasses is different person in terms of these five criteria. This is quite, not straightforward, right? Okay, now let's check different features like the headscarf. It varies much significantly compared to the glasses. So this is quite weird, right? Okay, maybe it is because of the different actions or different situation. So let's check some same interview, but with different background. So this is the same video, but this background is added by some post-processing. I mean, these two videos are identical, but this background is added by human. And again, this with picture changes a lot. I mean, the machine changes a lot its score by the background. Okay, when it changes to bookshelf, it again changes a lot. So this is weird again, And the last one is brightness. So this is just different camera setting, so different filter. But machine thinks these two videos are quite different in terms of these five criteria. So this is quite weird in terms of the our desired feature. So we expect that the machine interviewer is reproducible and objective, and it is not biased. But we see that this machine interviewer is quite biased to the appearance and backgrounds and other visual features, So at least for this case, we can think that machines are not, not like what we want. So let's check why this happened, by back to the basic of the machine learning. So this is how machine learning works in terms of the training. So when we have data point X and label Y, machine just give us some prediction. So let's say this machine say this cat is Santa Claus. In this case, we fix the model parameters to make the predictions correct. When the prediction is correct, there is no update. Of course, in practice, it is more complicated, but in high level, you can think this is what machine learning works. Then when does circle learning happen? So assume very simple toy example. So this is a binary classification, whether classifying car or boat. So every car in dataset is on road, and every boat in dataset is on water. So machine think, both images have water patterns and car images have road patterns. So when we give strange images like car on water and boat on road, model think this is boat and this is car, because machine think boat is based on this water pattern. So, but the answer is correct in terms of the annotation. So this model predicts correct answer, right? So there is no update because the prediction is correct. But the model only attends on easy shortcut to solve the original task. So in this case, we say shortcut learning happened. This is another very interesting example to how the shortcut learning happened. So yeah, assume there are 3 different types of classes. So first one is red small circles, and second one is medium size green triangles, and the last one is large size blue square. Okay. So this, what is the class of the small blue triangle? Okay, let's check in person. I think this blue triangle is class 1. How many? No? I think this small blue triangle is class 2. Oh, quite many. Okay. And I think this blue, small blue triangle is class 3. Okay. So from this very quick case study, we can think that humans are usually biased on shape, right? So this is a kind of test for what feature is actually focused by humans or machines. So we can doing same test on machines to check which feature is focused by machine. Well, so we check that humans are biased or focusing on shape, right? But we found that we can find that machines actually prefer recognize object by colors. So so if our task is focusing on color, so color is a desired feature. In this case, machine do not suffer from the shortcut learning because machine predict based on the correct feature, right? But if our desired feature is shape, then machine suffer from the shortcut learning because machine choose undesirable, easy to learn shortcut. In this case, color. So we say in this case, shortcut learning is happened. What does it mean? So shortcut learning or easy to learn shortcuts or desired feature is actually defined by humans. So it is defined by task, defined by data set, defined by some evaluation metrics. But machines, have some specific preference on the data set or the task. So if we do not make some alignment between our desired task and the machine preferences, shortcut learning will happen. If we do not consider any, some advanced learning strategy or some advanced annotations. So this is another example for more realistic example. So this is for face data set, and we can see that the machines are mostly focusing on race feature and gender feature. Okay, so this is summary of part one. So I just introduced the circle learning problem. This is happening around the world. So there are a lot of examples of circle learning. And circle learning problem happens when the model makes a decision based on undesired feature, not desired feature. And naive learning strategy will lead to circle learning if we do not consider what is the desired feature for the given task. Okay, this is reference, and yeah, do you have any questions? So this is end of part one, and okay, thank you. Could you pass mic to?
Yeah, unfortunately, that's the only mic.
Okay, so this is only mic. So could you just say the question and I will repeat?
So my question was that there was a bit of conceptual drift in the focus of your play. When you it starts off that the topic officially is the shortcut, but then when you introduced the test done by the interview and personality model, the focus suddenly became bias. And you started with a big assumption, and probably very few people in this conference make that you're right, and maybe people outside of this conference will make, namely that the AI is supposed to be unbiased. So yes, if you want to use that example for biased decision making, certainly. But if you want to use that example to show that it's using shortcuts in a way that makes it very different from humans, then the example is not, I don't find it so persuasive or so shocking. Because I think each of the biases that probably very trivial and superficial test for personality exhibits are very common in humans too. The first case in which the interview wears a glass, I guess we humans do it all the time. That's why it's so important how we choose what to wear, especially if we go to interview. Don't ask me if someone does not consider this, and you're not considering this because you want to be considered a fashion model, but because of the bias this can create, including on personality traits, which was what that was trying to guess. The effect of background, like the picture, actually humans are also influenced. I think if you take two humans and ask them to evaluate candidate for personality, and you put red background in a red room or in a blue room, you get something like that, probably as much difference as that. So in a sense, is this really showing shortcut? I think this is showing much less than a shortcut. This is showing a bias, which probably if you do a human versus AI comparison will not be higher than what the human would be. I mean, that's a guess, but I would like to see.
Okay, so I think the question is about the difference between shortcut and bias. And most examples in this talk, the first part is about bias, right? And you think using examples of some biased model is not proper to describe what is shortcut learning, right? Okay. Yeah, I absolutely agree. Because this shortcut learning is quite a broad area. I mean, because we define shortcut learning like the machine just make decision based on undesired feature. So it means that if machine is biased, it is again shortcut learning happen. So I don't want to say that this is everything in some This is not only way to describe this phenomena, but I want to say that this is a type of different lens to understand what is happening around this biased AI. Well, I think it makes sense too. Anyway, so yeah, so it okay.
Yeah, so I was actually kind of having a similar question, and like this example with the banana
Mhm.
makes perfect sense for how it's just using something like color as a means for making this decision and kind of taking that shortcut. I agree that it would seem a little bit less clear on the interview style scenario, but you could also imagine maybe a situation where somehow the model learns like that glasses are the proper feature for a strong assessment in the same way that this is learning just yellow for banana. I don't know if it was actually doing that in that scenario, but like I guess that might be a way to kind of like map it together a little bit.
I think the point is that you should wonder, like, would a human not also be biased
Right.
from seeing the results? Probably they were.
Right.
And so it's undesigned for different reasons. Like here, if you include a lot of green bananas in the data set, then the label would still be the same, and eventually the model would unlearn shortly. But I think in the interview example, the labels for the human would find would be different because they would also bias like Johnson. And so then the fix would not be to just include more data.
Right. Yeah, I agree with that. Thank you.
Yeah, thanks for the question and answers. Let's check the hoping. Okay, I don't think there is question from online attendees. Okay, thanks for your questions, and I think we have to move to part 2. Yonghan will present understanding short learning through the lens of causality and invariance.
Okay, so everyone can hear me? All right, so thank you very much, Sanghyuk, for presenting the first part. And I'm going to present the second part, which is the topic is on understanding short learning through the lens of causality and invariance. My name is Yonghan Jung, and I'm in Purdue University. This is my website. And there is a tech report for this part, and it's available for our tutorial website. So if you're more interested in this topic, please check. And this is a kind of light talk that I'm not going to go really in deep, but I'm just try to, convey the idea that what I want to say. All right, so let's first focus on the motivational example for short learning. And we go back to the topic, we go back to the example of classifying the images of the boat and the car. Okay, so we are given the data set, which is that the boats are on the water and the cars are on the road. And the machine learning model will train a decision rule, or will learn the decision rule for classifying the boats and the car. And then the model will classify for a new image, which is that the boats is on the water, and the machine learning model will classify this as a boat. All right, but as we just covered from the previous part, the modern machine learning models oftentimes make a mistake. But if we are given a new set of the image model, it's possible that the model wrongly classify this as a car. So what's going on here? And these mistakes happen when machine learning model use unintended and undesired feature. For example, like a background feature in our example, as their decision rule. Like, let's be more specific that we are given the data set and the model trained in the way that, oh, if there is a water, then this is a boat. And if there is a road, and this is a car. And because like we kind of assume that like most of the images that we collected, boats are usually in the water and cars are usually on the road. So it works pretty well for the training data set. However, when we are seeing the new example, which is that the boats are on the road, oh, and there is a road. So model makes a mistake. And this is kind of recap from the previous part. So here's some definition, like not really a formal definition, but like kind of the informal version of the definition is that the short-term learning is a phenomenon where the machine learning model fails to generalize for a new image, like new sample, due to taking unintended, undesired feature called shortcut in establishing their decision rule. So for the questions that asked by the audience is that, I agree that like short-term learning, there are not much definition because it's very subjective concept, like what is unintended, what is undesired. But there are some specific sets of the desired features that we want to use. But if model fails to use these features and makes a mistake, then we consider this as a shortcut. It's kind of the very subjective definition. All right, so this was a recap for the short-term learning. And this is an overview of this part that I will provide a formal understanding of the short-term learning through causality. And I will, sorry, not I, but we, we will propose two approaches for preventing short-term learning, which both suggest using causal features. I'm going to, explain what that is later. And two approaches is that let's avoid the causally irrelevant features to the true label as much as possible. And the second approach is that let's find the machine learning model that works well for all heterogeneous data generating process. And don't worry if you don't understand this, because I'm going to go detail and explain like what the words mean. And finally, we will provide some principle for identifying causal features by leveraging causal invariance property. Okay, so this is an overview. And let's go to the first item. We want to, I first want to note that we can actually express the data generating process as multiple functions. So for example, like if we have a data in the label that the boat is in the water and the label is a boat. And data generating process, we can assume that there are multiple functions that generates the background object like water. And there are functions that generate the boat object. And there are functions that generate the label object. So we can express the data generating process with multiple functions. And this view can be formalized as something called structural causal model that is given by or developed by Professor Judah Paul. And Judah Paul 2000 is his seminal textbook called Causality. And structural causal model formally is defined by the tuple, which is that V is a set of the variable, like observed variable, and U is a set of latent variable, like a hidden variable, and F is a set of the functions determining the value of the VI. And the P probability U is a distribution or uncertainty measure over the latent variable. Okay, so this is the formal definition of the structural causal model, or I'm going to call it as just SCM. And SCM can be used as a description of the data generating process. Like for the previous example, like there is a function that generates a background object. There is a function that generates a target object in here both, and also a function for generating the label and some distributions over all the variables. And it generates the data. And one thing that I want to note is that instead of accessing or any knowledge of the function itself, we usually assume that there are some qualitative description of the structural causal model, which is that commonly in terms of the graph. All right, and one of the power of the structural causal model is that it can encode the intervention on the data generating process. That's the one power of the structural causal model. For example, right, so from the previous example that the background object was a water, but suppose that we just intervene to force the background object to be the road, right? We just manipulate the data generating process and just force the background object to be the road. This gives the image like that. The boat was the same boat, but now the background is a road. And graphically, this intervention formally is something called do operator by Judah Paul. And it's graphically, the intervention is expressed as cutting all the edges, all the incoming edges. Like for previous example, the background object, there is a okay, can you see the mouse pointer? Yeah, there is a background object and the U was and there is a edge from U to D, and now these edges are cutted. Okay, so the structure causal model, like from the previous, the structure causal model induced by such intervention is something called sub-model of the structure causal model, like a sub-model of the SCM. So more formally, for the structure causal model M, the sub-model MVI is the SCM induced by replacing the function that determines the value of the VI, FVI, and replace this as a fixed constant. And this is the formal definition of the do operator. And what we saw is that on original image, which is that the boat in the water, and some perturbed or adversarial or just changed image, boat in the water, boat in the road, they can be viewed as objects generated by structural causal model and its sub-model. And this is what people call environments, or which is that the set of the structural causal model and their sub-models. And we assume that these environments are the data generating process of the given samples. So now with these notions, we can formally define the problem as follows. Our task is to construct a machine learning model working well for all environments. And like this is a diagram that given the, for each of the environments, we are given the samples that are generated by each of the environment. And what we want to do is to build a machine learning model from this data that working well for all environments. All right, so now we cover now we will cover that we'll propose two approaches for preventing shotgun learning. And we first cover the first approach that we will let's avoid the causally irrelevant features to the true label as much as possible. So before we are going to the first approach, we want to first cover that how do humans classify? Let's consider this image that the boat is on the water. And there is a boat and there are water, and this bidirected edge is some kind of this is a way of representing the correlation. And like human, even a baby, see this a boat object and classify this image as a boat. Oh, there is a boat. And for this perturbed example, that boat is now on the road, and yeah, there is a boat and there's a road, and the baby also classify this as a boat. I'm pretty sure that baby can actually classify this because I have a 3-year-old baby. I tested this with my baby yesterday, and he actually classified this well. No, I'm seriously. All right. So one lesson from this observation is that humans don't use background, like unintended, undesired objects, in classifying this. Then what about the machine learning model that is contaminated by the shotgun learning? With the same image, the machine learning model use a boat and the background object, which is undesired and unintended feature, and classify this as a boat. But since these background features are used importantly for making the machine's own decision rule, it is possible that machine learning model can classify this as a car because there is a road image. And this water or road, which are background features, they are causally irrelevant, or they didn't cause human's decision. So they are causally irrelevant features to the human's label. And machine learning model use these causally irrelevant features for their decision making, and that's one of the reasons that they actually fail. So now let's relate short learning and causally irrelevant features. So previously we said that short learning is a phenomenon that machine learning models fail due to taking unintended or undesired features. And from the previous example, we can rewrite this as a model fails due to taking causally irrelevant features to the label, which is made by human, for their decision rule. And this rewritten short learning notion gives our first approach. Hey, then let's avoid the causally irrelevant feature as much as possible. So then what is the causal irrelevance? Causal irrelevance. And we say that a set of the variable x is said to be causally irrelevant given other information w if intervening on x, like do x, it doesn't affect the y given do w. And this is a formal definition, is that the set of variable x is said to be causally irrelevant to y if intervening on x to some variable, some value, or x to other value x dash, and doesn't change the value of the y given other information w in terms of the probability. Oh, and this causal irrelevance is defined in terms of the w. So without w, we can say that like x is a set to be causally irrelevant set. Oh, there should be a set here. X is a causally irrelevant set to y if given the other rest of the variable intervention on the rest of the variable, intervening on x doesn't change to the y. Or as more formally, x is said to be a causally irrelevant set if intervening on x and given the intervening on other variable like v minus x and changing the value of the x to x dash doesn't change the value of the y. So this is a causal irrelevant set. And here are something interesting things about the causally irrelevant set when we are interpreting the meaning of this in the graph. And before introducing, we first introduce something called causal feature of the true label. Okay, if you're familiar with the causal graphical model, this is just a parent of the y. But if you're not interested in, if you're not familiar with the structural causal model, it's like the former definition is that if PAY is called causal feature, if there is a graph induced by the structural causal model, and then PAY is a set of the parents or direct cause of the true label. And graphical interpretation of causal irrelevant set is that x is said to be causally irrelevant if x doesn't contain any causal feature. So this is the one interesting thing, is that if x doesn't contain anything, like anything in the causal features, then it's causally irrelevant. Okay, so this is an example that, okay, because now the both object is a parent of the label both. This object is a causal features, but this water object is not the causally irrelevant. It's causally irrelevant set because it's not the parent of the label. And also the same, like both is a causal feature, but the role is a causally irrelevant set. Okay, so formal interpretation of now we are introducing the formal interpretation of the approach one. That informally, approach one says that let's avoid the causally irrelevant feature as much as possible. But let's be more formal. And what we know is that the largest causally relevant set is a v minus PAY, which is all variable except the causal feature. Therefore, to prevent the short learning, let's construct the models using causal feature PAY because we want to avoid the causally irrelevant set as much as possible. That means that we have to construct the model using causal features. Right, so now let's cover the second item, which is that approach 2, find the machine learning model working well for all heterogeneous data generating processes. All right, so let's recap our task that we wanted to construct the machine learning model working well for our environment. And our approach 2 is based on this task, is that let's find the performant machine learning model that working well for our environment, even in the worst environment, like both in the road or both in the space or whatever. So let's be more formal. That the task can be written by some math, which is that this FV is a machine learning model, Y is a label, and LFVY is a prediction error. And what we are interested in, the quantity of interest is the expected loss of the prediction model to the label. And the worst environment is given by the probability that in the environment, or like this environment set PE. And our goal is to find the machine learning model F that minimize the expected error even in the worst environment. That our goal is to minimize the expected error even in the worst environment, that is max P. And one of the interesting results is that model with causal features works well in the worst case. Okay, so this was our task. And if the loss function is given by the regression, like mean square error, then the solution is the expectation of the Y given causal features, meaning that we have to learn the relation between the true label and the causal feature. And in the classification task, like this one is a indicator function, then which is commonly used in the classification task. And the solution is also given by the relation between the true label and the causal feature. So the machine learning model working well in the worst environment can be found by constructing the model for the relation of the true label and its causal feature. That's the takeaway. Yeah, so let's construct so some implication of the approach 2 is to construct a machine learning model using causal features. So far, this is a kind of intermediate summary, is that our first approach was that we have to avoid the causally irrelevant features. And second approach is that we have to find the model working well in the worst environment. And yeah, I was quite interesting when it both suggests that we have to construct the model using causal features for preventing the shock learning. So now let's cover our final items that find the principle for identifying causal feature. One thing that I want to note first is that identifying the causal feature is quite difficult because like causal feature is a parent rule of the Y, which is parent in the graph. But if we don't have a graph, then identifying this is quite hard. So how can we identify the causal features? So to identify, we first introduce the property of the causal feature, which is called causal invariance. So let's go back to our example. And what we can see is that for the original image and the perturbed example, the relation between the boat and the label, like the baby boat, they are preserved. I mean, they are the same. Like even if we change the background, like boat is in the road, boat is in the space, but still the relation of the boat object and the label are the same. So informally, the probabilistic relation between the label and causal features are invariant over all environment. This is the property called causal invariance. Or let's be more formal. Like under the assumptions that y is not connected by bidirected path, or there are no hidden variable between there are no hidden confounder between the y and the other variable. For any environment, M1 and M2, the probability induced by the environment for all probability induced by the environments, the relation between y and the causal features are the same. This is something called causal invariance. And so we are introducing the test function for deriving causal features from the invariance property. That our observation is that finding the invariant set is actually easier for finding the causal feature PAY, because, for example, for all environments, if there is a good estimator for the conditional probability, then check for given the x, checking the probability y given x, and if they are the same, then x might be the invariant set. So there are some kind of measure. There's some way to test that some sets are invariant or not. And another approach is that using the conditional independence test, that if x is invariant to y, if y and the rest of the variable are independent, condition on x. So yeah, this is the example of the test function. And we say that some test function is a t, and given the environment, x and y. And the test function is a function that outputs 1 if the relation between the x and y is invariant for all environments. So using this test function, one thing that we want to note first is that causal feature is the smallest set satisfying this passing this test function. So if we have a good high probability test function that captures the invariant set in high probability, then the smallest set passing this test is the causal feature in high probability. Yeah. All right, so now let's summarize what I have been talking so far. That to prevent the short-term learning bias, we consider two approaches. The first approach is to avoid the causally irrelevant features. And the second approach is to find the model working well in the worst environment. And these two approaches give one lesson that, hey, let's use the causal feature for building the model. And we say that the causal smallest invariant set is a causal feature in high probability. So take-home message is that to prevent the short-term learning, take the smallest invariant set for our environment and build a model. All right, so this is a summary, even if I gave a summary so far, sorry. Yeah, we formalize a problem using the structural causal model, and we propose two approaches and have the same conclusion. Construct the model using causal features, and identifying causal features are hard, so let's use the smallest invariant features. All right, thank you very much for listening. And now I am taking some questions. Yes, please. Oh, wow, thank you. Oh, yes, please.
Very basic explanatory, so the non-causal explanation. So the variables. So why, what is caused? Are you defining y to be what? Is y? So I'm sticking to your example of the boat in the lake. Okay. So is y being a boat? Is y being a boat picture? Is y being what most human beings would classify as a boat? Is y being, I don't know. Yeah.
Y is just like a label. Yeah, I mean, Y is a label, and in here, I mean, Y is not the picture of the boat itself, but Y is like a label, kind of the can be described as a number or text, like a short text.
X.
X is a, X is a data set itself that we want to classify. So kind of machine learning input. So Y is an output or label, like a true label, and X is an input.
So now, if you go to your definition of the initial definition, you say causal feature. No, the one that you had afterward, when you said less formal one.
Well, let's form
I
one.
find mathematics Python. What you're understanding as a causal feature is something in the data which causes the, when you said that Y is a label, which causes the label.
Yes.
But
Okay, please go ahead. Sorry.
That's what follows from the definition you gave. So X is something in the data, and you said that Y is the label.
Yes.
But is this really a causal relation between the two?
Yes, I think that there is a causal relation because when there is some oracle like a human, when we see something like X, some images, and we put the output based on some of the features, which I call the causal feature. So this causal feature actually causes the output.
Okay. So Y actually is the image being classified by a human. That's what you mean by the label. Y means
What?
is called the effect is the picture being classified by most humans or whatever humans were used to label the data. That's your Y. That's the effect. And X is input data, typically picture data of humans and interpreted as an image.
So in this image, so your question is that in this image that this blue cloud is a Y? Is that what you're asking? Because what I want to mention is that this, this one, like the true label that made by the human, this is a Y. Yeah. And because this object causes human to say that this is a boat, so this is a Y and this is an X or a causal feature.
That's incredibly important.
Oh, yeah. I mean, I'm so sorry for making this or arousing this confusion. Sorry, and thank you very much for this pointing out this one. Any other questions? Yes, please.
I have a question about the formal X. When you describe the relationship between X and Y, we treat the X as numerical vector, right? Because the data is
okay. Yeah.
And normally, when you have an example about an X, its X is described as something, the object.
Like an image.
Yeah, image or maybe I can say the prototypical object, like boat or the water. But actually, I think there is a between gap between the numeric vector and the prototypical example. So when we just try to doing some experiment to showing some these short of learning. So what do you think about how to treat the X to show this kind of situations? So what do you think about the how to deal with the formal X? So do you think it is necessary transform the numeric vector X to represent the sophisticated human interactable object, or just you still think that it's possible to connect the x and y relationship just itself the x as the numeric vector?
No, I mean in this tutorial, in this part, actually, I didn't like how to say classify or distinguish that x is a numeric data or x is an image, and this is actually the task because how would I say? I think that causal inference. Causal inference is mostly developed for the numerical data set. And so there should be a task for making the image data to the numeric data, which is that for making machine to understand the causal inference with this framework. And this is some task of the people call like a representation learning. And actually, one of the interesting thing is that this is the topic for the next part. So please stay tuned. Thank you very much for the question. Yes, please.
I'm curious about how about the performance algorithm when we use only the causal feature for your model. Because for me, I think shortcut feature or shortcut pattern are often quite useful information for the model.
Sorry, could you? I couldn't hear well.
Yeah.
So.
Yes. I am asking about like how about the performance algorithm for the model when you just apply the causal feature, because for me like the shortcut features also is quite useful information for the model to learn, because in most of cases you can see in the data set that the balls on the water is obvious.
Yeah.
It's more the cases of that kind. So it's in like so the performance overall is that classifier works well, but just a few cases, we try to focus on some kind of valid one. And so how about we have another case overall? How about that accuracy? That's my question.
So I understood your question as that. Okay, so using the causal feature itself actually can do harm for the performance of the machine learning model, because it's possible that background features can help the performance of the model. Yes, and actually our task here is that for all possible kind of even the adversarial perturbation in the structural causal model, how do we make the model that kind of works well in this setting? So in this specific task, like I kind of propose that we have to use a causal feature, but if we have just a subset of the sum model, then it is always possible that using the non-causal feature also can help the performance of the model. So yeah, so I think that there are some recent works that uses the causal feature, and the non-causal feature, like as a regularization, is also one possible candidate that people are considering, I think. So, but if our task is that considering all possible submodels, then still, then as we shown here, then the solution actually implies that we have to learn the relation between the true label and causal features. Yeah, I hope that this answers your question. Okay, thank you very much. And
can you put the definition of the how do you call it, the test of robustness that they're using, the one in terms of the least favored environment? Who could you put that slide?
Oh yeah, like this one, right?
Yeah. Okay. So now that you gave that definition of why, now I have a doubt about definition of the worst case, and I'll try to make it with an example. Suppose that you have a picture of a car that looks like a boat, but it's a car. It has four wheels, and it's actually a car that looks like a boat. and it's on a street. And suppose that the human tends to misclassify this pretty bad because we're not very good at looking at details, and also because we don't attach probabilistic weight to the context that probably in a way is proportional to its increase in probability. And the machine, it's one of those cases where if you don't do anything in terms of causal learning, the machine actually gets it right because it attaches a lot of weight to that stream. And so that contributes to the correct classification of the car. So when you want a model that works best in the worst case, do you mean a model that classifies that image as a car? That is what actually is in the picture, or as a boat, which is what a human would label.
Thank you very much for an interesting question. So your question is that, let's say there is a boat, looks like a car, right? But in that case, like if we're, as a human, like if we just saw that boat, like the boat looks like a car, but we cannot really classify it accurately. But in that case, we can classify this correctly because even if the boat looks really like a car, but it's on the water, so oh yeah, this is a boat. This is a boat even if it looks like a car, right? And I think this introduces a new scenario, a new interesting scenario in the sense that, okay, so our previous example, yeah, it was quite obvious that we consider only a boat object, right? But in that new example, even the human, use the boat object and the water object and make a label. So in that new example, the background is no more causally irrelevant feature, I think. So now it causes the label. So in that case, like now the background is also a causal feature. Yeah.
It doesn't answer my question, but it answers a better question that you didn't ask.
So any other questions? Okay, so if we don't have any question, I think sorry. Oh yeah. So now the part 2 is over, and what's the next? Okay, now then we are taking the break for maybe 15 minutes.
Yeah, I think we're running a little bit late, so do we want to come back at 5:15? Right now it's
10 minutes? 10?
10 minutes? Okay, so yeah,
10?
maybe right now it's 5:10, so is the meeting here at 5:20? Okay, we'll just be running 5 minutes late.
Okay, then yeah.
Everyone?
Yeah.
Okay, we'll do 10 minutes late. Well, thank you.
Yeah, please come back at like 5:20 then. All right. Thank you very much for listening.
I thought that would be definitely not. That's hard to see them. The size, no, because so yeah. It's easier. Yeah, it just takes a little bit. Oh, yeah. Well, it covered a lot of the things we saw, especially with the using results from people that have racial bias. I guess the more important part was having people. That part was okay. They did mention about some sort of data augmentation, set of data. Yeah. 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 But yeah, I think it's a there's so it's not just facial recognition. I mean, that's mostly that's the most direct bias we can think of. But there can be other types of biases like religion. That one I don't think is gonna be accurate because it's not just facial recognition, but it has to be like the background surrounding the person. Your clothing, your background, it's taking some sort of thinking that we probably don't recognize ourselves as machines. Yeah. So there should be some but can't be where that data is coming from. There's, that was this issue because with so many non-linearities going on, there's this thing around transformers where a lot of the people in the industry thought they were interpreting the machine by looking at the attention spans. Right. So there's this one paper that says that's all yes, and you can't really interpret it based on the attention because actually do have stereo tasks. Yeah. You have drastically different generations. I took that up also and TV. So like the pictures that they showed about like the attention being called some spaces like the cat that might not be so so there must be some more scrutiny actually I don't think we can just naively say, oh, it's actually not just based on right. You might be able to just apply some not so visible noise on it and get the grasp of it. Then it's just nonsensical to say that's interpreted. There's the possibility that the most statistically reasonable answer would be that it's a banana seal. Yeah, that paper I think was so what it did was it assessed different values so what it did was basically gathered 100 different ID sizes actually measured how societal needs.
was like, the more the merrier.
Okay, now 5:20, then I will start about part 3 right now. Okay. Okay, I will start part 3 right now. I am Kyungwoo from University of Seoul. Okay, pay attention, please. Thank you. I will start about the part 3, the learning invariant representation. I am Kyungwoo from University of Seoul. In this talk, I will cover the learning invariant representations. First of all, we will review the concept of the invariant features. To get a competitive performance for all environments, including the most disadvantaged environment or the worst environment, we should construct the invariant features. And we will denote the invariant features as PAY. Let's think about the table data example. We bring the table data from the other data set, one of the benchmark data set for the fairness. The task is to determine whether a person makes over $50,000 per year or not. Let's assume that the parent of Y, the invariant feature, are occupation and hours per week. For the table data set example, if we know the PAY exactly, then we just select the PAY features into our machine. Then our machine can predict the label Y correctly based on the invariant features. Let's think about the image and text data set. Maybe you will already familiar with the car and boat examples. The first case is to determine whether the object is the car or the boat, not the background. And the second example is to predict whether the hair color is a blonde or the black. And the third example is to determine whether two sentences have a contradiction relationship or entailment relationship. Let's see each examples in detail. First example is to determine whether the object is a car or a boat, not the background. As we saw earlier, when we train our machines, that kind of data set only, then our machine will focus on the background data set, because the background is the distinct features and it is enough to minimize the training loss. However, as you know, the background is not the invariant features. The invariant features are the object. Therefore, the machine will fail to predict that kind of image correctly. The second example is to determine whether the hair color is blonde or the black. We bring the examples from the Cellup A dataset, one of the benchmark dataset for the computer vision related task. Among the dataset, most female has a blonde hair, while male has a black hair. Therefore, our machine will focus on the gender to predict whether the hair color is blonde or black. However, the gender is not an invariant feature to predict the hair color. Therefore, our machine also fails to predict the hair color of the right image. Our machine will predict the hair color of the image as a black because the image about the male. Let's think about the sentence. we bring the examples from the MNLI dataset, one of the benchmark dataset for the NLP. The task is to determine whether two sentences have a contradiction relationship or the entailment relationship. Among the dataset, most contradicted sentences have a negation expression. Therefore, it is enough to focus on the negation expression to determine whether two sentences have a contradiction or entailment. However, we know that the negation expression does not cause the contradiction. It is not an invariant feature. Therefore, the machine will fail to predict that kind of sentences. For example, the little girl is sad and the girl is not happy. We know that two sentences have an entailment relationship. However, our machine may classify it as a contradiction because of the negation expression. In short, what we want is the invariant features. How can we make our machine focus on the invariant features, the PAY only? For the table dataset, it is relatively simple. If we know the PAY, the invariant features exactly, then we just select that kind of columns and injecting it into our machine as an input. Then the input is only about the PAY and our machine can only focus on the invariant feature. How about image dataset? How can we extract the invariant features only? It is not trivial. Let's think about the image case in detail. As you know, the left case is to determine the object. The object is an invariant feature and the background is not invariant feature. In that case, how can you only extract the invariant feature, the both object, without the background? It is not trivial, right? The right case is about the rotated MNIST dataset. The task is to determine whether the digit image 0 or 8. The digit features are invariant features, and rotation angle or the thickness is not invariant features. However, it is also not trivial to extract the digit features only without rotation angle or thickness features. Therefore, for image case, for the image dataset, we usually inject our input image, all of the input image into our machine. For the image dataset, we usually adopt the neural network-based feature extractor and the classifier. And we expect and we wish that the extracted features H contains only about the invariant features. However, in reality, the extracted features H might include the undesirable features, such as the background. It may cause the problem. In short, what we want is to make our extracted features H only contains the invariant features, in that case, the both object. How can we make our machine only focus on the invariant features? How can we make our extracted features H only contain the invariant features, such as a both object, not the background? The most intuitive approach is a data augmentation. Let's think about the examples. The left images are our training dataset. as we saw earlier, if we train our machine on the original data set only, then our machine will focus on the background, non-invariant features. However, if we can augment the data set to generate diverse data set, such as car on the water or boat on the road, then our machine can focus on the invariant features. If we train our machines on the diverse data set, then our machine knows that the background does not indicate the label anymore. Therefore, our machine tries to focus on the object, the invariant features in this case. Let's think about the more realistic setting. Can we really generate that kind of image easily? We only have a small image such as boat on the water or the car on the road. In this situation, generating that kind of diverse image such as boat on the road and car on the water is not trivial. The data augmentation is not always possible. Therefore, we need another approach instead of the data augmentation. Another approach is to regularize the representation or the model. Let's assume that we have two environmental data sets. First environment is about the boat on the water, and the second environment data set is about the boat on the road. Later, we will regularize that the representation H only focus on the shared features across the environment. In that case, the invariant features, the boat. We summarize the three problem cases and their approaches. First problem cases is that we can generate diverse data set from the augmentation. And the second problem case relaxes the data augmentation assumption. If we cannot augment the data set, then we will utilize another approach, the regularization-based approach. We will describe it later. And lastly, the third case assumes that we do not have environment label or the bias label, as well as the data augmentation. From now on, I will describe each problem cases and approach in detail. This is the first problem cases when the data augmentation is possible. I bring the rotated MNIST data set, and the task is to determine whether the digit image is 0 or A. As you know, the invariant features are the digit, not the rotation angle or the thickness. We want our machine only focused on the digit image. To learn the invariant features, we will generate diverse rotated image. Given 0 image, we can rotate that image 50 degrees or the 90 degrees freely. We can generate diverse data set easily. After we generate diverse data set, make our machine run on the original image as well as the augmented data set image. And we will introduce some invariance constraint to run the invariant features. The first approach is to constrain the output. The left image is the original image, and the right image is the rotated image, the augmented image. If we introduced the constraint to make the output of the left image and right image is the same, then our machine can produce the same output, whether the images are rotated or not. And another constraint is the representation constraint. Instead of the up constraint, we make the extracted features from the original image, and the rotated image is the same. For the generative model case, such as variational autoencoder, it can be interpreted as the posterior regularization. And the third approach is to average the output. When we have two output, the first one is the output of the original image, and the second output is the second one is the output of the rotated image. We utilize the average output as our final prediction. Then our model can predict the same output, whether the image is rotated or not. Let's think about the more realistic settings. Even though we can augment the data set to generate diverse images, the optimal data augmentation policy might not be known, right? A human knows that the suitable rotation angle for the digit 6 is from minus 90 to plus 90, right? If we rotate the digit 6 image 180 degree, then the image is changed to 9. It is not suitable, right? Then how can we make our machine know the optimal data augmentation policy automatically? There is a way to run the data augmentation policy itself. For the rotated MNIST dataset example, we should run the suitable rotation angle. And we let the rotation angle as the runnable parameter zeta. This method have two kind of object. The first one is the classification loss. The classification loss minimize the image, whether the images are the rotated or not. And the second term is the regularization loss. To avoid that the zeta degrade to simply just 0. When the runnable parameter zeta, the rotation angle becomes 0, then the regularization loss becomes large. It is noted that there is a minus sign. Therefore, we can minimize the regularization loss more if the zeta is larger than 0. Another example, when the zeta becomes to unusually very large values, such as 180 degrees, the rotation angle, then the digit image 6 is changed to 9. However, the label is still 6. Therefore, the classification loss might become large. Therefore, by minimizing these objective functions, we can run the suitable data augmentation policy, zeta. Until now, we have focused on the case 1 scenario, where the data augmentation is possible. However, as we see earlier, the data augmentation is not always possible. It is not trivial. When we only have a boat on the water dataset, it is hard to generate the car on the water dataset. From now on, we will cover the case 2 scenario, when the data augmentation is not possible anymore. to get a high level idea, we will assume that there are two environmental data sets, both on the water environmental data set and both on the road environmental data set. And we will assume that we train each data set independently. Then there are 2x2 cases, whether the feature extractor learns the object or the background, right? There are 2x2 cases. And as you know, the ideal case is that both feature extractor focus on the both object, the invariant features. It is the ideal case. When two feature extractor learns the invariant features, then the optimal classifier for each environment will be the same, because we just classify the invariant features both as a both. Therefore, when our two feature extractor learns the shared features, the invariant features, then the optimal classifier for each environment will be the same. We just need to classify the both object as a both. The natural question is, what if the optimal classifier for each environment are the same? If the optimal classifier for each environment should be the same, then both feature extractor should focus on the invariant features. So the main idea is that let's make the optimal classifier for each environment as the same. From the high level idea, the invariant risk minimization, the IRM introduced the constraint optimization problem. The IRM has two components. First one is minimizing the traditional training loss for each environment. And the second one denotes that the optimal classifier for each environment are the same. Then, as we see earlier, we can make our feature extractor focused on the shared feature, the invariant features. In short, the IRM introduced that kind of constraint optimization problem, and as you can see, it's not trivial to solve the problem. There are some multiple optimization loops. So there is an approximated version, the IRM V1. This is the final objective function for the IRM. IRM V1, the approximated version of the IRM, also has two components. The first component is the traditional training loss for each environment. And the second one is the regularization loss. The gradient of the loss with respect to the classifier. Minimizing the regularization loss denotes that we reduce the classifier sensitivity for each environment, and it induces that it makes the classifier for each environment, the optimal classifier for each environment, make the same. Okay, from now on, I will cover another approach to solve the problem case 2, when the data augmentation is not possible anymore. Another approach, instead of the IRM, another approach is a group DRO. Let's think about the two environmental data set again. In the usual case, among our training data set, the number of environmental 1 data set will be larger than the number of environmental 2 data set, right? The boat on the water and the boat on the road. And the left environmental data set will be larger than the right. Therefore, if we make our machine run that kind of data set, then our machine will focus on the environmental 1 data set, because the number of environmental 1 data set is larger than that of environmental 2. In that case, as we see earlier, our machine will focus on the background, not the object. It may cause the problem. How can we solve the problem? The main idea is that make our machine focus on the environmental 2 data set instead of the environmental 1 data set. If we make our machine focus on the environmental 2 data set first, then our machine can run the invariant features. Let's assume that our machine still run the non-invariant features such as background. Then the training loss of our machine will be low on the environmental 2 data set. Okay, there is a background and there is a boat. However, in that case, our machine will fail to predict the label of the environmental 1 data set because there is no relationship between the road and the boat. It is noted that the number of data set of environmental 1 is larger than environmental 2. Therefore, the average training loss will become large. Therefore, to minimize the average training loss, our model starts to focus on the object, the invariant features. This is the high-level concept of the group dialogue. The principle of group dialogue is that let the machine focus on the most disadvantaged environment, such as environment 2 in that case. And we can formulate the idea as follows. However, there are some limitations for the IRM and group dialogue. For the IRM case, as we saw earlier, we approximate the IRM, right? And besides, the IRM is not theoretically guaranteed on the nonlinear settings. Group dialogue also has some theoretical limitations. Group dialogue only consider the training environment and its interpolation. Besides, IRM and group dialogue only access to the training environment. Therefore, when we encounter the test environment that are sufficiently different from the training environment, then we cannot guarantee anymore. From now on, I will introduce the empirical limitation of the IRM and group dialogue on the waterboard dataset. Waterboard dataset also has 2 components, background and the object. Waterboard on water background and landboard on the water background and waterboard on land background and landboard on land background. And as you can guess, the most disadvantaged environment is the anti-diagonal, landboard on the water background and waterboard on land background. In that case, the group dialogue improves the most disadvantaged environmental accuracy compared to the vanilla model. However, the disadvantaged environmental accuracy is still lower than that of average accuracy. Besides, we found that the extracted features, the learned features from the group dialogue, still contain undesirable features. When we classify the background based on the extracted features, we can easily classify the background the undesirable features from the representation. It denotes that group DRO, the extracted features from the group DRO still contain the undesirable features. We can see the similar case for the IRM. In short, we found that empirically, IRM and group DRO still contain undesirable features empirically. And there are many recent papers that report the empirical limitation of the IRM and group DRO. And the last case is that when we do not have an environmental label, how can we utilize the IRM and group DRO? As you can see, IRM and group DRO assume that there is an environmental label or the bias label. However, in many cases, we only have a X and Y, not environmental label. So annotating the environmental label is expensive and it could have a privacy issue. In that case, how can we run the invariant representation? So one of the idea is to infer the environment label. Then how can we infer the environmental label from the data set? There are two approaches to infer the environmental label. The first approach is to utilize the IRM principle. As you can see, the IRM principle is that all environments should have the same optimal classifier. In that case, the difference between the environment will be reduced. It denotes that if we maximally violating the IRM principle, then the difference between environment will be large, right? Therefore, we can infer the environmental label for each instance. Another approach is to utilize the group DRO principle. Group DRO principle is that the most disadvantaged environment has the highest training loss. Therefore, we should focus on the disadvantaged environment, right? It denotes that each environment has a different training loss curve. Therefore, we can infer the environmental label from the training loss curve for each instance. This is a summary of the part 3. In the part 3, we cover the diverse method to run the invariant features, such as data augmentation or IRM and group DRO. However, both approaches requires environmental label or some specific assumption. Besides, both approaches still contain the undesirable features. Therefore, we think that learning invariant representation is a still challenging problem. Because of the time limit, we only cover the main papers. However, there are many recent variant papers. So if you have an interest, please refer to the taxonomy and the reference. Thank you for your attention. Is there any questions?
Could you please help me to somehow understand the difference between shortcut loading and auto-distribution detection in context of car and ball example? Because in a way, it seems like what we actually want is to generalize auto-distribution rather than learn a shortcut. Because when I think about shortcut learning, it seems like we know it model is cheated somehow, that it learns what it was not supposed to. And when I think about it, it seems to me like we can judge if it did or not. When we learned the model was inherently interpretable, so and then you can say, oh, okay, you're supposed to learn that, but you actually learned it. Otherwise, it seems like we just want to generalize to other environments.
So the question is actually covered by my next part. So please stay tuned for, because because this is very important question, and I think this question is actually the most important question among this talk, maybe, because how to evaluate or how to measure whether social learning is happen or whether social learning is actually solved is actually still open question. I think even if we consider social learning as some generalization or debiasing, I think it is still open question. So I will introduce some benchmarks. I mean, in terms of the data sets or problem scenario in next part, about 10 minutes. So maybe please ask a question if you still have question after taking my talk. Yeah. Okay. Oh yeah, please. By the way, we only have about 20 minutes, so yeah. Yeah, please go ahead. Yeah.
I'm thinking about how incredibly stimulating this is for advancing the fairness debate. So I'm thinking about an adaptation. For instance, one problem of fairness that I just imagined in one of the talks this morning was disability discrimination. And I used one example. So if you consider, for instance, a person with Asperger or ADHD, that person may have behaviors that in neurotypical individuals are predicted or associated with lower levels of intelligence or lower levels of motivation on the job. So if you have something like learning by shortcuts, the risk is that basically you'll be very unfair to this individual by predicting his qualification relevant features like motivation or intelligence based on factors that for that person are in a sense unfair as a standard to judge that person. So it seems that your framework could be so, and this is also very interesting because to frame this in terms of the typical categories of group fairness, it's quite complicated. We don't have they're not protected groups. In addition to that, even using the concept of disability is problematic because if you've got a high functioning Asperger or ADHD, it will not be disabled basically because it will compensate on many metrics. So one interesting application is that one could adapt this concept of environment versus cause to try to deal with some of the new possible fairness models, fairness problems. So for instance, a possible interpretation could be that in the context of predicting who's a good candidate, we should select the process that has more invariance, where something like being neurotypical versus neuroatypical is treated as environment. So I think that it will be really interesting when we start moving from both and background examples to other examples, how really we end up thinking about this concept of the cause and the concept of environment, and also think that we really need to understand that how we trace this distinction has very much to do with values, with what we value, what we want to value, what's pertinent. And so just, sorry, it's not really a question, it's more like, wow, this is really, I think, relevant and thought-provoking for the friendship.
Okay, thank you for your very valuable feedback. And today, for today's presentation, we prepared the example about the both and the part because it was intuitive example for us. And actually, there are many diverse examples, as you say. I also believe that that kind of imbalance can be applied to the fairness or other things. So after the presentation, I would like to discuss with you furthermore. Thank you. And if there is no any questions, then the Sanghyuk Jung will present remaining part.
By the way, Yeah, by the way, the organizer said it is actually should be ended until 6 p.m. right now, but it is physically impossible. So I'm going to skim around the last part. Actually, it is very short. I think it will take about less than 5 minutes if we skip some slides. So this is actually a recap of the previous slides. And it is actually the same as the last one. So we have to, because of some, convenience, I just say that bias label, but you can think this is as environmental label or something. So if we have additional annotations, then we can solve this problem, short-cut learning or bias problem. But actually, this is almost impossible to always get these types of additional annotations. So this last part is talking about how can we mitigating the problem, even if we don't have enough additional annotations. The first one is, and also it is actually I want to say, so collecting more data points is very expensive or even impossible because as Kyungwoo's last slide, most of the uncommon samples or decorrelated samples are very, very uncommon. And it is sometimes almost impossible to gather all types of such data points. So we have to consider different types of things like estimating bias labels or environmental labels using some method like predicting bias labels for using very few samples. And actually, this is the most important part I want to say. It is not always make some annotated bias labels. So bias labels are not always easily determinable. So for instance, this case, the VQA sample, VQA example again. In this case, the short-cut learning biases are not able to be annotated. So we know that this VQA model is biased to the text, or it only uses shortcuts on text features, but it is impossible to annotate what is the case of the bias or environment for this case. So in this case, we can use some debiasing with biased models. And it is a little bit technical, so I'm going to skip this part because it is quite intuitive and it is quite interesting in terms of some technical research questions. But because we don't have enough time, I'm going to skip this part because the next part is much more important. And by the way, we already published our slide as well as recorded video. So if you are interested in the last part, please check our tutorial homepage and the slide, please. So I'm going to skip this part because the most important part. Oh, okay. So this is, yeah, sorry. Okay, so most important part is, I think the most important part is here. So how can we, actually ensure that a model actually avoids short-cut learning? So it is quite controversial because how can you define short-cut learning is actually defined by task or defined by human. So there are several, relative benchmarks to measure, similar phenomena. So I'm going to check two different tasks here. So first one is called domain generalization, or sometimes called out of distributed generalization. So this is actually the same, benchmark with our last question. What is difference between short-cut learning and out of domain distribution? So I can say that this is one example of measuring whether model only focusing on desired feature or undesired feature. Because usually domain generalization methods assumes that we can learn some domain invariance feature because the domain information like sketch, cartoon, or art painting information is undesired feature for our target task in this case. So in this case, the target task is classifying whether dog or horse or on any other target classes. But these domains are undesired feature. So because we define short-cut learning is a machine determines the prediction based on decision based on the undesired feature. So You can check some domain generalization benchmark. This paper is actually from last iClear. Previous year iClear 2021. So you can check that the theoretical value-founded methods are actually underperform than the vanilla method in terms of the general accuracy. So it means that we are still, we need a large improvement for this area in terms of the algorithm. And the other example is cross-bias or de-biased generalization benchmark. So this benchmark assumes that the bias and labor are highly correlated, and during the training and and at the test time, the correlations are decorrelated. So I bring some intuitive example to compare what is the difference between cross-domain or domain generalization and cross-bias generalization. So cross-domain generalization assumes that every labels are available and different domains are accessible during the training. But we test the data points with unseen domain or unseen environment. So this is what we expect for out-of-domain, out-of-distributed generalization. And this is what we want for debiasing. So every class is correlated to some specific predefined bias. And at the test time, we remove the biases, and we expect it still works well in the debiased or decorrelated test sample. So there are a bunch of different types of benchmarks for measuring whether the machine actually focusing on desired feature. So this is an example. But I want to say that they are a kind of still toy question, toy scenario. So it is actually far from our actual realistic applications. So I want to say that it is still open question in two terms. First one is collecting perfectly debiased data set itself is very extremely difficult because the collection itself is very difficult. So we have to pay attention more about data set construction as well. And the other one is the scenario for how the bias or domain or any other shortcut features are correlated to the target label is still quite open question because there could be a lot of different scenarios. I think each of us has our own scenario for how to build these types of shortcut learning problem, right? So it is quite important to think about how can you measure these how can you measure whether a machine actually learns some true causal features instead of the uncausal features. And it should be controllable and reproducible benchmark. But this benchmark is still not, in my opinion, we have to more focus on how to build this benchmark. Okay, so this is my last message. Shortcut learning is defined by humans. So each of us has different definition of shortcut learning, maybe. But we define shortcut learning as model does not make a decision based on desired feature and undesired feature. But this desired or undesired feature itself is defined by human. So human determines which feature is desired or undesired. So it is very important to consider human during the development process of these machine learning models, like the making algorithm or dataset construction or evaluation, or maybe evaluation metric as well. So this is the last slide. How can we, avoid shortcut learning in practice, your own scenario? So I want to say that we have to consider from the data collection. We have to make the data set to be avoid undesirable data set biases. Also, we have to annotate more annotations or bias labels to avoid or to learn some invariant features. And this is the last slide, please. And we have to consider more algorithms. I mean, we have to design algorithms should be unbiased. And we have to consider, I mean, even if we design or we make some perfect algorithm, if we don't have good evaluation protocol, it is worthless. We have to focus on how to build more scientific and precise evaluation protocol. And last one, we have to consider humans during developing machine learning models or evaluating the machine models. Okay, sorry for the delay, and I want to get some questions, but I think organizers do not allow. Oh yeah, yeah. So if you have question, I think we can get one more question if the question is very short. By the way, is my last part answers your question? What is the difference between? Okay, thank you. Okay, so
Oh yeah, so this is the last, and so thank you very much for taking this tutorial. So this is a tutorial website like Fact22, Shortcut Learning, and in here you can access to the presentation and the technical report and everything, and the recorded video, and our contact. So if you have any more questions, so please contact us. Yeah, feel free to contact us. So thank you very much for listening.
비슷한 부분이 있어서 좀 많은 질문이 앞으로 저는 그 디지털학습 포스테이션 했을 때 그 전에 디지털학습 하면은 인베딩 벡터를 넣거든요. 모든 인베딩 벡터를 설명하는 관심이 있어요. X랑 Y의 릴레이션십을 해주셨는데 디지털학습에서 X가 얼마나 Y에 영향을 미치는지 그거를 X 저는 모두의 연결성이 궁금해서 중요한 모두 이웃 모드, 서브 모드가 어떻게 결과에 영향을 미치는지 얼마나 중요한 이거를 관심이 있고
in terms of the general machine learning, in terms of general machine learning. Okay.
Is that a correct question? Is this a question? How long does it take?
I think so because I just briefly introduced what is basic of machine learning here.
Yes, say for example, to train a machine to know a cat.
Mm-hmm.
How long does it take? Because I really I'm not familiar.
Yeah.
And so there was an example of 0 and it's sort of like 10 grams. And then we talk about how you talk about the best that it might not be accurate, is that right? Or it's rotating. So for a machine to understand how the 0 whether it's rotating at a certain angle. So do you have to encode every tiny details to the train?
Okay.
To make it like it's to make it identify that it's 0 and it's
So I mean, conceptually yes, but in practice, we let the model learns from the data. So that is what machine learning people say.
So you just put the code.
Yeah, just so it is how it happens. So assume this cat image is about 100 million vector, like the numerical values, like 0, 1, 2, 0, 0, 1,
So
2.
you say
Yeah.
0, so it be that picture, 0.1, it be that picture. Is that what you're saying?
No, I mean the pixel itself is the pixel value. So it is actually three-dimensional vector because there are RGB, right? So every color, one color is represented by red, green, or blue. Intensity of the in practice, yes. So that is how computer shows us some image, right?
I don't know.
Okay. Yeah. Okay, so that is how it goes. So every data point can be vectorized, which means that we can change some being numbers. I mean, any data can be changed to the some being numbers.
Who does that?
Sorry?
Who does that? Who can?
Who does?
Yeah. Like, do you do that?
Maybe fathers of computers, maybe, because that is how computer works. Computer represent everything in digital. It means that everything is number 0, 1, 0, 0, 1, 0. Yeah. So it means that every data can be represented by computer is actually changed by numbers.
Yeah. And it's like, who does all that? Like, is it an encoder? I don't know if it makes sense. So, who what do you call a person that does that? Is it a statistician?
Sorry?
So who does that? Do you call it a statistician that do all the data coding or grade the image or something?
You mean?
Say, for example, to make it capture that, who does it? Like, what type of person is that?
I mean, who starts this one, right?
No, I mean,
Or,
like, say for example, a medical doctor.
Mhm.
And so a medical doctor, if you have a problem with a heart, you go and see a cardiologist. So who does that? You do?
So, I mean, computer do.
Yeah.
So how computer do is, so
Yeah, I kind of know what you mean. The computer only do it because we put the thing, right?
mhm.
So who puts the thing?
Humans, of course.
Yeah, but
Yeah.
what type? You know, like,
So,
what's the...
so this is everything, we make some data samples as number, like the, so for instance, language. So we can change language as number
Yeah.
by,
So is it like a statistician or just ordinary computer guy? Can you do that? Like, I mean, of course you can.
I mean, maybe,
You, right? You can do that. Because you
yeah,
can do
I can do, but there are previous works do similar thing, of course. So, some computer guys, I mean, some computer, it is usually done by computer science or machine learning field. So I can say that some machine learning stuff not basically focused on theoretical thing, because machine learning itself is actually based on the very hard mathematics and theoretics. And actually our talk is mostly about some theories usually. But there are, of course, some practitioners who want to solve some problem in practice. So there are some people in this area. But I mean, this area is machine learning.
That's what I wanted to know.
Well, there are a lot of people. I mean, for instance, right now, at the same time, in New Orleans, the biggest computer vision conference is now happening, and in the conference there are more than 6,000 people. I mean, most of them are. I mean, I can't.
What do I call it? Like, what do
Well,
that's what
I don't. Okay. I never think about.
Because
I
that's what I
never.
want to know. Like,
Yeah.
because you want to do that, but you don't want to understand that. So that's what I want to do. That's like here. So what would I call you?
I don't know. Just a person.
Yeah, but it's
Yeah.
just a person. If that is a cat, you have a name.
Well, maybe someone can call computer scientists or computer engineers.
So yeah, that's what I want to know. So,
Mhm.
so the computer scientists, computer engineers, you all work together to play, right?
Yeah, kind of.
That's what I
Yeah.
mean. And you are the two computer scientists or engineers or the statistician, the mathematician.
I'm not mathematician. I'm not statistician. I'm not, doing very hard mathematics right now. So I'm more like computer scientist and computer engineer, in between of
So
scientist
you
team.
are the computer engineer. Now I understand. That's what I wanted to know.
Okay.
Yeah. So
Because in computer science, it is difficult to exactly classifying what is science and what is engineering, I think. And sometimes engineering itself is very it could be scientific or
so does the computer engineer, do they also put the mathematical theory or in code? Say, for example, the movement of the zero or how that, so do they also encode it? Or do they create or it's already created? Oh, okay. Okay, I'll better don't ask you any more questions.
no. I mean, I'm thinking about because
But your presentation, the whole is very interesting. I was never from the II. I'm from the international law background. And I was asked to examine how automation is used in my country. And I had to understand this. It's really interesting because you kind of like, so you don't look at things anymore from one perspective. You also get to learn to look at it from the other perspective. And that's it's very interesting.
Thank you.
Thank you.
Yeah, thank you very much.
Sorry, I'm gonna leave you.
All possible background features.
Yeah. So you're kind of eliminating the environment problem.
네네.
하시는 분들이 많아요. I just want to ask a very quick that.
Yeah, I mean, so do you know any, or can you recommend any of the smart way to do the data augmentation where we don't have any environmental level?
Yeah, exactly. This is the question because I'm not sure if there is a way or it's.
What is your application? I think it's usually based on the application. I mean, it is very ad hoc to your.
Right now I'm studying a task that is called selective classification, which basically what it does is selecting some instances where the classifier is not certain enough, and it just avoids predicting in that case. And so I was wondering whether if you apply this to this thing, we might detect what are the instances that actually trick the model, or if there is a connection. I was wondering.
It is usually domain specific. I mean, if your classifier takes some image input, there are a lot of image augmentation methods, like different lighting or mixing different samples.
Yeah, but I'm more referring to which are the features that trick them. Well, not the features, the examples that trick the model. Like, can we intervene, like maybe augmenting those examples that trick the model?
Okay.
And then maybe you can retrain the model in order to avoid it.
Okay, do you want some practical answer or some theoretical answer?
What do you prefer? Like,
I mean, in theory, you can make some adversarial samples.
Yeah, exactly.
Yeah. So I can say your question can be solved by adversarial samples by making some adversarial. So assume you have some differentiable model, and your objective function is differentiable.
Yeah.
You can
make that.
Yeah, right.
Just to maybe dance or whatever.
Yeah. That is. most theoretical and academical answer, but it is not work in practice in my previous experiences. The other way is you could
Yeah, because from a very pragmatical perspective, I was thinking that those instances are those where the classifier should be less certain, like because maybe he gets that there is something going on, like the background is not the same compared to what he is always used to classify. So I was just wondering, it was just a curiosity.
it is quite
Like because for how I see it, like it's when you have images, you have like all the features, but nobody takes it for granted that the goal is on like the first 5 pixels, maybe not even it's on the last 7 pixels, and it's all about identifying it, in a way.
yeah.
So the trick is that one.
It is non trivial.
Yeah, exactly.
Because training, it's quite well known that machine learning models are overfitted to the data. And it is also well known that the machines are overconfident to the training set. So if you just apply some traditional way to learn this training data, you will get very high confidence data.
Yeah,
There are no guarantee. Of course, you can get some lucky chance to less confident one. So it's quite important. If you want to check some uncertainty estimation, it's quite important to what do you want to capture by the uncertainty. So there are some different ways to define uncertainty. If your uncertainty is measuring whether this sample is correct or wrong, or maybe difficult or easy, I think the only way is change your objective function as well as the input. There are, in practice, people use the label smoothing method. The label smoothing method is, I assume you already know about how machine learning models are trained on stochastic gradient.
Yeah, from
okay. Then do you know label smoothing?
What?
Label smoothing.
No.
Okay, so this is how label smoothing works. So assume we have 10 classes.
Okay.
We usually use that. Okay, this is class 1, 2, or 3, right? And we apply the torch mode, test for whatever.
Yeah, torch. Yeah.
Apply to number of and your target and prediction, right? This is what we do. So this target is just one of those, right? What label smoothing does is change this one and let's say this is 0 base because we are computer science. Instead of 0, 1, 1, 1.
You have the probability. Okay, so
assigning this.
That's exactly what we are doing. It's the softmax thing again, but also for the time.
Yeah, right. So this is for the labels.
Yeah, I didn't know that.
This is quite famous technique on deep learning method to make more generalizable and less confident. In practice, this is work not the best one, but usually works very well. So I think this is the most important one, the simplest baseline. Just apply your method to learn with less confident target. So you can check this label smoothing.
Yeah, because I guess if you apply this with in order to find the causal, I'm not sure, but I guess that there might be something like you have the training data, maybe you have the car on the road. It's fine. I guess it could be super easy. But when it has a boat on the road, probably this should might help.
So this is some general explanation,
Yeah, yeah.
and if you want to know about how to make some device method, then
근데
not the most
일단은
famous
여기서
most
아이디어는
popular one, but I think one of the mainstream
저희가
is making your
만약에
own
X가
model.
PAY라면 모든
And assume there exists some bias model, and make
X가
them
만약에 causal feature
like the so one way is make the method
그러니까
be
X라는
independent of each other.
포인트 자체가 의미가
So
없어요.
it means that your target model, of course,
P를 찾을
you
때
have to
모든
make
로스를
your target
로스를 가장 맥시마이즈하는 P를 찾는 방법인데
with the
인풋이 causal feature는
so
어떤
your
P를
task
택하든
is should be solved by your target model, and as well
probability
as
Y
your
even
model should be
PAY는
independent with
모든
the bias
인바이러먼트에
model.
대해서 똑같기
Yeah,
때문에
or the other way is so this is
causal
more
feature를
mathematical.
택하게 되면은 그냥 인맥스, 미니맥스
Yeah,
문제에서
different types of
그냥 미니마이제이션 문제로
heuristic is
그래서 X가
so this is
PAY일 때는
assume
미니마이제이션
your data is
문제로 가기
and
때문에
assume some of
미니마이제이션
them are
문제에서
biased,
클래시피케이션
and
로스일
some of
때는
them are
PAY,
fine. Yeah, so
PAY,
some good things. So
리그레션,
there are some ways to
그게
figure out what is
아이디어.
bias.
그러니까 어떤
And whenever
인바이러먼트에서
you find this
디스트리뷰션이 나오는 PYD는
these
PAY는
types of methods apply some
그래서 맥시마이제이션이 의미가 없습니다.
Yeah, that's it's very similar to what I'm. Yeah, this thing is very similar to what I'm currently studying. It's basically finding instances where the model is not confident enough and avoid from predicting on this.
네, 근데 예, 말씀하신 포인트는
It's
되게
a similar
재미있잖아요.
practice,
실제로
it's not that. It's learning to do it.
F가 인 제너럴하면 미니맥스의 클로즈 펑션을 체크해보죠.
Yeah, whether you apply that to this context empirically, because I don't know if there is a theory behind it. We could be able to detect those instances that are reaching the model and then maybe preventing them and retrain the model or like the generative version of
원래 그래프가 만약에 있으면 사실 아무 문제가 없어요. 인바이러먼트가 그래프가 없거든요. 그래프가 있으면
Yeah,
PAY 일도 아니니까. 근데 그래프가
is more
없을
balanced
때
because in the end it's a problem of
저는 일단 태블러 데이터를 선정하고 이야기를 하고 했었던
so there are
이미지라고 하면
many different methods for how to make some device model from this one.
그냥
Some
만약
models
스프레드शी트
remove this one. And just learning with this method. So this is very primitive version of it.
this and then the best setting is the highest version of the data.
Yeah.
네네네네.
Sometimes.
이산 데이터.
But if our method actually
근데 이산
for
일단 벡터 뉴메리컬
it should
벡터로
be
나오는
work well as well as the original
디스크리트하거나 컨티뉴어스라고
I mean even for device that is conceptual.
이미지랑 대비되는
But in practice, because we remove the data points, it usually degrade the performance. So people now use using full data set, but less analyze, using some weights for these samples. So that is more listen to it, I think. Yeah.
그래서 좀 중요한
so I
포인트는
can
여기서는
recommend
인바이러먼트를 스트럭처 코저 모델에서 나오는 그러니까 모든 가능한 그러니까 스트럭처 코저 모델이 약간 썸 모델이라고 해서 스트럭처 코저 모델을 조금씩 변형한 애들이 있는데 걔네들에서 데이터가 나왔다라고 가정을 하면
You can get some
그 가정하에서 그러니까 인바이러먼트라고 했을 때 저는 그걸 인바이러먼트라고 가정한
and it is actually
거기에
If it's in the site, I'll check
스트럭처
it.
코저 모델에서 뭘 어떻게
Yeah, it is in the slide here. So this one, the first one. Yeah, this one. So what this one is bias is easy to learn feature. So it will memorize very early stage. It first train model very short time and train the another method and another model by selecting some bias completing samples using this biased model. So that is how they do this part. And then they apply some generalized entropy, which makes some different weights based on the logic value or the loss values of biased model. So biased model makes some weights for the biased model, and the biased model will be, the target model will be divided using the generalized cross entropy. So that is what this paper argues.
네, 근데 스트럭처 구조 모델에서 나왔다는 것은 제가 생각보다 센 가정이 아니고요.
Yeah, good starting point for
스트럭처 구조 모델
how
정의 같은
people
것도
solve this
빼고
problem.
그냥 어떤 한
Or if you want this type of independence, you can
어떤 우리가
you can check my paper. Yeah, so this paper is mine. So we apply some. So point is that how can you apply independence between two models? If they are not random variables.
Exactly,
And,
that's
yeah,
a very good question.
So that is how. So there are some method named Dilbert-Schmidt independence criterion. Not this company. Okay, independence test. So this is some statistical test of
The graph, okay.
yeah. So it is not based on the random function, but based on some samples from two random variables, and it is a statistical testing whether two sampled values are independent or correlated. Yeah. So and they are differentiable, so we can use them as some loss function. So that is what we did here. So you can check the code, not the paper.
Thanks a lot.
Yeah.
It was very nice to.
Yeah. If you have any other question or if you want to,
Yeah, we will. I guess I'll write.
yeah, please send me some email.
Thanks a lot.
아, 예, 예, 맞습니다.
세 개가 있고 저희가 모든 이미지를 내는 모든 이미지는 우리가 존재하는 이 월드를 어떤 식으로 좀 캡처하는 거잖아요.
맞습니다.
그 월드가
네네네.
하면 여기서 6포인트 약간 처럼 6포인트는 모든 세계가 어떤
근데 되게 정확한 이게 실제로 그 코졸리티 비더펄에 스트럭처 코졸 모델 하면서 이게 그냥 실제로 그 책에 적혀 있는데 그것도 가시 있어가지고 이게 네이처 모델이라고 이렇게 하거든요. 그래가지고 그 네이처 모델에 대해서 실제로 가시만 이렇게 얘기했을 때 그때 어떻게 변하냐 그런 식으로 얘기를 하기 때문에 굉장히 정확한 이게
오라클이 들어가고 아드버서리얼이 들어가면 그냥 그렇다라고 하죠. 그래서 좀 스태티스티컬이 아니라 좀 더 트레디셔널 머신러닝에서 아드버서리얼이라고 하는 거는 아드버서리 이그젠플 얘기하는 게 아니라 인바이런먼트에 대해서 어떤 오라클이 있어서 딱 대입해가지고 그중에서 월스트 케이스 뽑았을 때도 분석해야 된다 하는 거가 원래 아드버서리얼의 의미였거든요. 근데 지금은 오라클 없이 그냥 프레젠트가 때려가지고 아드버서리얼이라고 하긴 하지만 원래는 그거는
스케일 때 뉴비인데 이번에 루이스 쓰면서 보고 있어요.
이쪽 길 들어가지고
이 쇼컨 디바이스 아니 무슨 이제 제출을 한 거니까
그래도 목차 되셨으니까 뭐 축하드립니다.
근데 사람들이 계속 지금 의외로 저도 이게 사장님 처음 소개받을 때가 송경훈님이 소개를 시켜줬는데 그러면서 저도 쇼컨 러닝이 뭐지? 이게 제일 궁금했고 그때 하면서 우리가 무슨 얘기를 하지 하는데 제가 누구한테 얘기를 계속하면서 저는 개인적으로 쇼컨 러닝이라는 컨셉 자체가 되게 정리가 잘 안 돼 있다고 느꼈거든요.
쇼컨 러닝뿐만 아니라 바이어스를 어떻게
아까 전에 나왔던 뭐 오드
네.
제너럴라이제이션 이런 것도 그렇고
그래서 네, 쇼컨 러닝 하면 이거는 바이어스이니까 이거는 오디
그래서 그 슬라이드 모든 디자이너보다 어떤 사람의 인텐션이나
네네네
이런 것들이 들어가기 때문에
그래서 그거를 좀 실제로 페이퍼에서 진짜 그러니까 쇼컨 러닝이라는 말을 처음 쓴 페이퍼에서 실제로 가져오기도 하고 그리고 모든 거를 다 설명할 수 있는 굉장히 포괄적인 컨셉이죠. 예를 들어서 그 아까 여자가 히잡을 썼던 뭐가 다른가 이런 거에서도 그게 페어니스나 바이어스 이그젠플이라고 사람들이 하지만 그리고 실제로 디자이어드 피처는
그 사람의 인터뷰 내용인데 인터뷰 내용 말고 외부적인 게 도입이 됐기 때문에 머신러닝 분들이 실수했다 이렇게 쳐버리면 쇼크노미이기도 하고 그래서 이게 제일 정확한
슬슬 정리를 해야 될 것 같은데 기념사진부터 하겠습니다.
저희 안녕하세요.
그러면
네, 저희 이거 배경으로
제가 선생님께서 다시 한번 저희가 무슨 상황을 이렇게
게임하는 거 같아.
왜 이렇게
살짝 벗어.
너무 떨어져 계시죠.
왜냐면 이렇게 떨어져 있어요.
온라인 맞춘 거예요?
디스트리뷰티드.
온라인 너무 힘들어.
찍겠습니다. 하나, 둘, 셋. 찍으면서
잠시만요.
네,
죄송한데 저도 직권으로 하나.
직보는데.
감사합니다.
아무거나 보내주신 간직하겠습니다.
그럼요.
알겠습니다. 따라가겠습니다.
하나, 둘,
감사합니다.
용실끼리 한번 찍을까요? 네, 의원님 노렸으니까.
내가 여기 가운데 딱 껴가지고.
저희도 마스크 뭐 어떻게 잠깐 볼까요? 잠깐 벗고. 좋습니다. 의원님 가운데로 오시죠. 네,
이거는 저희 거 아니죠?
네.
와, 크기가 미쳤다.
찍겠습니다. 하나, 둘, 셋. 하나, 둘, 셋.
감사합니다. 감사합니다. 고생하셨습니다. 의원님 오늘 그 블루티어까지 오늘 밖에까지.
네, 저 그래도